Hello and welcome back. This is discussion 6 for X370. And today I'm going to cover the finite state machine, single cycle data path, and multi-cycle data path. So first topic is about the finite state machine. So finite state machine consists of a set of possible states and rules for transitioning between states given the specific input. So first, for the finite state machine, we will have state. And in the state, we will have the state name. So let's call it 00, state 00. This is the name of this state. And usually in this course, we were talking about Moore machine. So the Moore machine, the output only depends on the state. So in the state, we will have the output. The output can be 0 or 1 or many bits. So let's assume the output is only 1 bit. So it can be 0 or 1. So we can have output 0 in state 00. This is our state, and we have the inputs. So the input, let's assume also a 1-bit input. 1-bit input can be 0 or 1, 2 cases. And given the specific input, we can have the transitioning between different states. So let's have another state so we can have transitions. Let's call it state 0, 1. And output here can be 0 or 1. Let's assume this is a 1. Given the specific input, let's say input 0. Input 0 will make the state 0 goes to state 1. And the output will change from 0 to 1. Also, we must consider all the possible inputs for a given state. So for state 00, we have 2 possible inputs. One is 0, one is 1. So now we have the input 0. But for input 1, we can, let's say we can stay in the same state if the input is 1. So we don't change to another state. And now for state 00, we have all the possible inputs. And we're good for state 0. And for state 1, we also have 2 possible inputs. So one possible input is 0. Let's say if the input is 0, we transit from state 1 to state 0. And also for input 1, we also go back to state 0. So that's for all the possible inputs, we go back to state 0. So this is a complete finite state machine. And a simple example. So for each state, we have 2 inputs. We have the state name. We have 2 transitions. We have the output for each state. And let's see a more complicated example for the finite state machine. So we are required to design a finite state machine for a bottom activated LED. The light should remain lit while the button is consistently pressed, or blink every 3rd cycle while the button is not pressed. So what's our input and output? So input is the button is pressed. So let's say if it's pressed, our input is 1. And if it's not pressed, the input is 0. So this is our input. We try to make everything into a binary format so that will be easier to draw the finite state machine. And what's the output? Output is light is on. So light is on, our output is 1. And if light is off, the output is 0. So this is our input and output. And now we can design the state and the transition between different states. So first, we can have an initial state, and the state, let's name it 0, 0. So the output here is off because currently we're not doing anything. And next, if we press a button, so the light should be on immediately. And we just go back to another state, and we can call it 1, 0. Let's call it state 1, 0. So the state 1, 0, here the light is on, the output is 1. So if our input is 1, we go to the state where the light is on and the output 1. This is one possible input for state 0, 0. And another possible input for state 0 is when the input is 0, we go back to another state. We go to another state. Let's call it state 0, 1. And in this state, the light is still off because we need to blink every third cycle. And this is only one cycle. Okay, so now state 0 have the output, have the name, have two transitions, and this state is complete, and we can go to the next state. So let's look at this state, the state where light is on, the output is 1. So in this state, we also need two possible inputs. Once the button is pressed, one is not pressed. So if button is pressed, we will stay in the same state because we want the line to be on. So if the button is pressed, we stay in the same state. But if we release the button, we will go back to our 0 state. The light is off. So from this blink, we have 1, 0, so 1 cycle not pressed, 2 cycle not pressed, and we need another cycle not pressed. So the light should blink again. So the third cycle, if we still not pressed, we will go to the state 1 because the light should blink at this cycle. 0, 0, 0, 3 cycles, and we blink again. And for the state 0, 1, if we press the button, if our input is 1, we just directly go to the state 1, 0. So no matter the input is 0 or 1, we always go to state 1, 0 in the state 0, 1. So that's our finite state machine. And the slides should be posted to the website. You can also check for the answer in these slides. And this is about the finite state machine. So after the finite state machine, we have all the hardware, like basic components we need for the single cycle data path. We have our combinational logic, where the output only depends on the input. We also have our sequential logic, like finite state machine or flip-flop, or the register files. So we have the basic components we need here for the single cycle data path. And the single cycle data path is the hardware we use to execute our instructions. So remember in LC2K, we have 8 different instructions, add, NOR, LW, SW, and so on. So but we still need some hardware to execute instruction. In the project, we only do a simulator, but this is in C, not the real physical things. But here we will try to build the data path. So we have our sequential logic, memory, register file, and reg. So this reg is PC. This will only change this value in the positive edge of the clock. And we have all the combinational logic, MUXes, 3 to 8 decoder, the ALU, arithmetic logic unit, and two adders and the sign extensions. So these are everything we need to deal with the data. And this is part of the data path. And another thing is called ROM. This is a control ROM. So part of our control path. And because we have 8 different opcodes, we still want only one data path, which can execute all the different instructions. So we are trying to reuse ALU. ALU can be used for add, NOR, LW, SW, and we need to select the different inputs for the ALU to do the different operations. So this is when we combine everything together, and you should have seen this diagram from the lecture slides. It's a little bit complicated, but you have to know it to do the exam. So let's first look at the control ROM, the component on the bottom here, the control ROM. So for a very simple example, we have the input on the right side, A0 through A2. So A0 is the least significant bit, and A2 is the most significant bit. So when we write it, we should write 0, 1, 1. And 0, 1, 1 is 3 in decimal. So if we have 3 bits in the input, we can have like 8 different, it can represent 8 different numbers. And because we start from 0, we go to 7. So this is a decoder. We have 3 inputs and 8 outputs. So the input is 0, 1, 1, which is 3. So we select the line 3 here. And the value for this horizontal line will be 1. This is our input. And when we have a black dot, like this one, when we have a black dot, it means we have a diode here. The diode will allow the current to flow in one direction. So if we have a current in the line, horizontal line, it will flow to the vertical line. So this vertical line will become 1. And our diode can only allow it to flow in one direction. So even if the vertical line is 1, it will not activate the horizontal line again. So we have the 2 diode in this horizontal line. So we have 1 here and 1 here. Also, there is a small typo in this slides. The small circle here should be this one. So if there's no black dot in this point, there's no diode, and they are not connected together. So only here we have a diode, and only the vertical line is high. So the vertical line will give us the output, and the output is 1001, the 4-bit output. This is our ROM, and we have a control ROM for the single cycle data path. So given the opcode of the instruction, we output the control signal for muxes, ALU, register file, and data memory. So this line, so these vertical lines, these are the output for the control path. And our input is the 3 to 8 decoder. This is our opcode. Okay, so we can simplify the ROM to the figure like this. So if we have the instruction add has the opcode 000. So if we have 000 to our control ROM, the output here will be 11111000. This is our output. So in the data path, we have 1, 1, 1, 1, 0, 0, 0. So in the data path is 1, 1, 1, 1, 0, 0, 0. This is the control signal to different components. And if our instruction is LW, LW will give 1, 0, 0, 1, 0, 0, 1, 0. So for LW, it will become 0, 0, 1, 0, 1, 0. This is the output signal for the control path. Okay, let's do an example for the instruction. So assume we have the instruction add 1, 2, 3. So add instruction. The first step will fetch the instruction and increment PC. So in the single cycle data path, we have 2 different memories. This one only stores the instruction, and this one only stores the data. So we read the data, read the instruction as the address PC. PC is a program counter, points to the instruction we are executing. So we read the instruction as the address PC. And in the same site, and at the same time, we increment PC. So increment PC is using the adder here. This will do PC plus 1. This is PC plus 1. This is our first step for add instruction. And next step is decode and set the control bit. So here we get our machine code, which is a 32-bit integer. And because our 31 to 25th bits, they are not used. All of them are 0. So we only use the last 25 bits. This is our opcode. And opcode will pass through 3 to 8 decoder, and decoder will set the control signal, which is 1, 1, 1, 1, 0, 0, 0 here. And in the decode, which means we just split it into different parts, we have the offset here. Offset field is not used by add, it's used by LW, SW, and BEQ. But we still have this 16 bits pass into the sign extent. And this is reg A, reg B here again, and the death reg. So it set different field to different bits from the machine code. Next step is read the register value. So we have the reg A and reg B. This is the input to our register file, and we know which value we want to read. So the register file will output value A and value B in this yellow line. Value A and value B. So now we get the value of reg 1 and reg 2. Next step is add them together. So to add them, we need ALU. And ALU will need 2 inputs. Remember, this is the output from our control path, control ROM. So one input is value A. It will directly goes from register file to ALU. But for value B, we need a mux to select whether we need offset or the value in reg B. So for add instruction, we need value B. And for mux, if we want to select the bottom value, the selection bit is 1. So the selection bit is 1, we use the value B. And we add them together. And ALU also have one control signal. And if the control signal here is 0, we do the add operation. So we add value A and value B. If the if the control signal is 1, we do the NOR operation. We do value A NOR value B. And it will always output the comparison result like equal, no matter we have 0 or 1 for this control signal. So here we have the control signal to be 0 because we want to do add. After we add them together, we have the A plus B for the output of ALU. In add operation, we don't modify the value in the memory, in the data memory. We will write the value back to our register file. So the value will go all the way back through this line to this mux. To write to register file, we need two values. First, we need to know which register we are writing. Next is the value we want to write. So this mux in the green circle, this mux gave us which register we want to write to. So we want to write to reg B, or we want just to write to des reg. For reg B, this is used by LW or JALR. In this case, we want to write to reg B. But for add and NOR, we will want to write to our des reg. So we select the second input to this mux, and the selection bit is 1. We want to write to des reg, and we want to write the value which is the output from ALU. So this line is the output for ALU. It's also the second input to this mux. So the selection bit is also 1 for this mux. And the top input for this mux is from the data memory. This is used by LW instruction when we want to write the memory, the data we read from the memory back to our register file. So this is everything we need to do for adding instruction. You can also try to go through the lecture slides and go through each instructions, try to understand what components they need and what they're doing in different steps. So this is a table that summarizes which component each instruction will need to use. So first is for add. When the instruction is add, we need to read the instruction first. So this is instruction memory access because we want to read the instruction first. And every instruction needs to read from the memory first, because we haven't know the instruction yet. So it's yes for array opcodes. So next is read reg. So do we need the register value for this instruction? For add, it's yes, because we want to do reg A plus reg B. And ALU is doing the add operation. But we don't need to access the data memory for add. We only write to the register file in the last step. So if you remember our control from output, the enable bit for data memory, this one is 0 because we don't want to access data memory. For NOR is very similar to add. We read the register value, we do the NOR operation, and we write back to the register file. We don't access the data memory. And for LW, if you remember what we did in the product 1S, the LW is reg B equals memory at address reg A plus offset. So we need the reg A value here. That's re-reg. And we need to do reg A plus offset. That's ALU operation. And we need to access the memory at this address. So that's data memory access. And finally, we need to update the value in reg B. That's a write reg. So LW will do all these operations. And usually LW is the longest instruction in the LC2K. So for SW, we have this equation. We need to read the value in register A and register B for SW. And we need ALU to calculate the address in the memory. And we store the value in reg B to memory. But we do not update any value in the register file. So there is no read reg. For BQ, we compare the value in reg A and reg B. If they are equal, we take branch. If they're not equal, we do nothing. Just go to the next instruction. So we read the value for reg A and reg B, and we use ALU to do the comparisons. And we don't access the data memory and no read to register file. JALR will read the value in reg A because we need to update PC. And we are storing PC plus 1 to reg B. So that's read reg. There's no need for ALU and data memory. For NOOP and HALT, they just do nothing. They don't require any register. They do not need ALU or anything else. So only they stop after read the instruction from instruction memory. And this is the answer for this problem. Okay, so after we understand what the single cycle data path for each instruction do, and we need to analyze the performance for our single cycle data path. So this is a very important thing when we design some data path. We want our hardware to run as fast as possible to use less time. So this is how we calculate the runtime. This is also called Aaron's law. And if you can see on the right side, we have time divided by cycle times cycle divided by instruction times the number of instructions. So if we trying to cancel the terms, we will have time equals time, which is definitely correct for this formula. So we just expand the runtime to different parts so we can try to minimize each part so the product can be minimized. So time divided by cycle, this is clock period. Like the time needed for each cycle. And cycle divided by instruction, this is CPI, clock per instruction, or cycle per instruction. So the last part is number of instructions. This is a program size. And in the single cycle data path, we cannot change this value. So this value is fixed by the program given to our hardware. So like the input file, the assembly code or machine code, you have like 10 instructions. This we cannot change. We cannot change it by modifying our data path. So in our single cycle data path, CPI will always be 1, which is the smallest between the single cycle data path, multi-cycle data path, and pipeline. CPI will always be 1, but the clock period will be very long. Because the clock period for the single cycle data path depends on the slowest instruction, which is LW. It uses all the components and it takes the longest time. So even for loop or halt, they will run at the same speed as LW because our data path can run all the instructions. So that's how we calculate the runtime for single cycle data path. And let's try to do a problem here. So assume we have 10,000 instructions. So this is a fixed program size. And ALU needs 10 nanoseconds. Accessing memory needs 50 nanoseconds. Register file read and write costs 5 nanoseconds, and everything else costs 0 nanosecond. And this is a percentage for all the instructions. But for the part A, we don't need this percentage because we have LW instructions. And all the other instructions run at the same speed as LW. So let's see how long does LW takes. If you check this table, LW will first access the instruction memory. This is 50 nanoseconds. And read register is 5 nanoseconds. ALU takes 10 nanoseconds. Data memory access takes another 15 nanoseconds. And write reg takes 5 nanoseconds. So if we add all this value, it will give you 120 nanoseconds. That's a clock period. (120 nanoseconds). And use our equation here. Clock period is 120 times CPI will always be 1 for single cycle data path, and times 10,000 instructions. This will be our runtime. And in part B, it's using the same time for each operation and the same percentage here, but it's asking about optimal achievable runtime for this benchmark. So it's assuming different instruction can run at different speed. So let's go back to this table. LW takes 120 nanoseconds, which will not change. But for add and NOR instruction, it only takes 70 nanoseconds. For SW, it takes 115 nanoseconds. For BEQ, it takes 65 nanoseconds. JALR will take 60 nanoseconds, and loop and halt only takes 15 nanoseconds. So assume different instruction can use different time. And we just multiply their time by the percentage of these instructions. So we have 25% of LW, and each LW will take 120 nanoseconds. We have 15% of SW, and each SW take 115 nanoseconds. So we just add them up, and this is the optimal solution we can get. But this is not realistic because we cannot change our clock period every instructions. So we only have one constant clock period for our single cycle data path. But the actual time needed is much faster, it's much less than our single cycle data path. So we're trying to minimize the runtime. And this is the reason why we have the multi-cycle data path, because we want different instruction to run on different time, because move and halt apparently will take less time than LW. We want it to take less time. We don't want it to spend the same time as LW. So that's why we have the multi-cycle data path. In multi-cycle data path, each instruction can take different amount of time based on the actual instructions. And our data path is restricted to have minimized the necessary components. So this is our data path. We use much fewer components than the single cycle data path. So we have one uniform memory. All the instruction and data are stored in this memory. But if you remember from the single cycle data path, we have instruction memory and data memory separated to two different parts. And we only have one ALU. So in single cycle data path, we have one ALU and two adders, but now we only have one ALU. So we use fewer components in our multi-cycle data path. And we only use one major component each cycle. So the major components can be memory, register file, or ALU. We only use one of them in each cycles. Or we can use two of them if they do not depend on each other. So let's say the time we can use two different components separately. So in the first cycle, we read the instruction memory and update PC. So update PC is PC plus 1. Our PC is here in PC. Go to this mux. And plus 1, we need 1 for the second input of ALU. So here we do PC plus 1, and we read from the instruction memory. So here we get our instructions. This can be done in one cycle because they do not depend on each other. So the input of the ALU is PC and constant 1. It doesn't depend on the output of our memory, so it doesn't depend on our instruction. And the input to this memory is PC, doesn't depend on the output of ALU. So these two operations are independently, which means we can use these two components in the same cycle. But if the two components depend on each other, let's say the read register operation and the read instructions. So to read the register, we need reg A and reg B value. So this reg A and reg B value are the output of the memory. So they cannot happen in one cycle. We have to separate it into different cycles. Even though we have enough components to use in our data path, we still want them to be in a different cycle because we want to minimize our clock period. Our clock period here will be the longest component, not the longest instructions. So for the single cycle, for the single components, so this is how many cycles each instruction will take. For loop and halt, on the right corner here, it only needs to fetch the instruction and decode. So after knowing these instructions, loop or halt, we will stop and fetch the next instructions because there are no operation to be done for them. It only takes 2 cycles. And add NOR, SW, and BQ, they will take 4 cycles because they need to read the register file, do the ALU, and like update the reg file again. For LW, it's the longest one. It will take 5 cycles. So it will read the register in the decode stage, do the ALU operation, read the memory, and update the register file. So this is how many cycles are needed for each instructions. And here we also have our control ROM, like the right circle. Here, this is the control ROM. But it's a little bit more complicated than the single cycle data path. Here we have the state. The input is the state. Like our finite state machine, the input is state. So the state 0 is a fetch, state 1 is decode. This is state 2 and 3 are for add, state 4 and 5 is NOR, state 6, 7, 8 is LW. So every time we just input the state number, not the instruction here. You have the state. And these 4 green vertical output, this is the next state. Which state we go next? If this is state 0, so next state will be state 1. If this is state 1, next state is depends on the opcode. And if this is state 2, like cycle 3 for add, the next state will be cycle 3, state 3, sorry, cycle 4 for add. So we give the input state to the decoder and we output the next state. And this part is the same as our single cycle data path. It's the control signal for different components, different muxes. And also we want to compare the performance of the multi-cycle data path with our single cycle data path. So our runtime is clock period times CPI times number of instructions. So this part doesn't change. This is the same as our single cycle data path. It depends on the programmers, the software engineers, of how their code is structured. But these two parts are different. So CPI is around 4 for multi-cycle data path. And clock period is very short because the clock period only depends on the slowest component, not the slowest instruction. Like LW use like basically 5 different components, and the clock period only depends on the longest component. But for single cycle data path, the clock period is long. It depends on the slowest instructions, which includes all the 5 different components. And CPI here is 1. So it's kind of a trade-off between clock period and CPI. We have a short clock period and high CPI. And in single cycle, we have a long clock period and very small CPI. So both of them are not the optimal solutions. So let's see the same, like basically the same questions before. We have 1,000 instructions, and these are the percentage of each instructions. ALU needs 5 nanoseconds, memory takes 15 nanoseconds. register file read and write takes 2 nanoseconds, and everything else doesn't take time. So the first question is, how many cycles are needed to complete this benchmark? LW, remember our diagram here. Only LW takes 5 cycles, noob halt takes 2 cycles, and all the other instructions take 4 cycles. So LW is 5 cycles, 4 cycles, 4 cycles, 4 cycles, and 2 cycles. So here we have 1,000 instruction times 20% times 5 plus 10% times 4 plus 35% times 4 plus 25% times 4 plus 10% times 2. This is the number of cycles we need to complete this benchmark. And total execute time is the clock period times the instruction times the CPI. So let's first look at CPI. CPI is cycles per instructions. So it's just number of cycles we get from the first question divided by number of instructions, which is 1,000. This is the CPI. And the total execute time is a CPI times the longest component, which is 15 nanoseconds here. This is the longest one. 15 nanoseconds times the number of instructions, 1,000. And this is the answer. We need 4,000 cycles. The execution time is 60,000 nanoseconds. And the CPI is 4 cycles per instructions. Sometimes you may find the multi-cycle data path takes longer time than the single cycle data path. Usually this is because our LC2K ISA is too simple. It's not used by our computers, like the laptop you are using. So it can happen when the multi-cycle data path, like performance is worse than the single cycle data path. But usually the multi-cycle will do better because we can have some extreme case where we have some weird instruction takes 100 cycles. So if all the instruction run at the same clock period as that longest instruction, it will be the execution time will be extremely long for the single cycle data path. So we can assume we have 1 instructions takes 100 cycles. And let's assume all the components just needs 10 nanoseconds. So in the multi-cycle data path, like if we have 1 instruction take 100 cycles, and the other 99 instructions are the noob or halt, so they only take 2 cycles. In the multi-cycle data path, it will become 10 times 100 plus 99 times 2. This is multi. And in a single cycle, you just say we have 100 instructions, and each instruction run at the slowest instruction, the time for the slowest instruction. So that's 100 times 10 nanoseconds. That's 1,000 nanoseconds. So all the instruction will run at 1,000 nanosecond clock period. So the total execution time will be 100 times 1,000. That's much longer than the multi-cycle data path. So usually multi-cycles will perform better than the single cycle. Okay, that's the last part for today's discussion. Thank you for watching.